would be about diffusion language models, and it would be presented by Valentin Malykh, who is a head for department at MWS AI. So let us welcome the speaker.
Thank you, Alexey. Hello, everyone, again. So, first of all, I would like to do some precautions since I'm giving this lecture for the first time in my life. You will be the first listeners, so you kind of guinea pigs, you know. Be happy with that. Okay, let us discuss in my person a few seconds. I have worked at Yandex, at Huawei, at VK.com. Now I'm with MWS AI, and I also have PhD in natural language processing. This is kind of my thing. The natural language processing and diffusions are really recent development in our field. So let us discuss them a bit. So first of all, I would like to see you to see this nice picture. It's like nothing fancy actually, but the important thing is maybe you aware that language models standardly, like in common way, they produce word by word. So they produce next word after given the previous ones. We call it left context. Okay, it's for most European languages, but for other languages it will be right context. Is really not important. But what is important here is that you see that these diffusion language models, it works in another way. It works like generating tokens whenever it wants. So if it wants to generate it right here, it will be done. It's not important when it, it has no other context around it. So it's just generating. So this is this stuff we'll be discussing today, but in a long story short, this is like called remasking. We'll discuss in details later. Okay, so let us start with the basics of diffusion models. I'm since this is really recent stuff, all the I'll be discussing to you, I'll be presenting to you. Actually, not maybe that recent, because this exact paper we are discussing right now is from 4 years back. But actually, no one cared about the diffusion language models until recently, until maybe a few months ago. And this is mainly because they are like worse, and they were worse in the quality. And I show to you the quality, how they measure it, and why it's worse. And more importantly, they are not only worse, but they also really slow, because you know the diffusions. The diffusions are slow, and for text they are also slow. Okay, so this is the paper, structured denoising diffusion models. And I would like to address you to this picture. Let us ignore the left part for a moment. And as you can see here, as you can see here, we have some generations. So we have the T128. Let us say this is the starting point, yeah? And after some diffusion steps, about 100, the most words are already here, but a few are masked. And at the time step 0, they are all here, I mean the words. So this is actually how it goes. So you have seen the GIF I have presented to you a few slides back, but this is like not in dynamics, but in details on the process. So this is how it's created. So we initially create all masks, and one by one, or in some other cases, many masks at one time, we like relieving it from the masks and getting the words. Okay, so few words about diffusions to better understand them. Thanks to Denise, who nicely presented the diffusions on the images and videos. But for text, it's in a kind of way, it's the same, but it's not like really the same. But let us start from the beginning. Yeah, you see that there is like forward process and backward process. Forward process for diffusion, when we add noise and it becomes more and more noisy, and it's obvious. But what is important here is that we have different, how could be said, the types or the different matrices, diffusion matrices they called, which we could apply to do the diffusion process. So in the center is Gaussian diffusion. I think Gaussian diffusion is well known to you, but in a few words, it's just simple Gaussian distribution, which is just applied, and given the picture, it becomes more and more smooth and noisy. But there are other types, and we'll be discussing them. It's uniform diffusion, and you see how it goes. So the uniform diffusion will have the only main diagonal on this matrix. For the Gaussian diffusion, you see that not only main diagonal, but also other diagonals are also used, but maybe less. And another one is absorbent state, so-called absorbent state. It's when you have the main diagonal and additional line of the I wanted to say attention, so of course it's not attention. It is the states which are they absorbs the probability, and you see this on the picture. And for the reverse process of diffusion, of course, it's the same. So we have the random noise here, and we apply some of these matrices to get rid of the noise and get to the original picture, hopefully. Okay. Let me start here. Yeah, unfortunately, that will be a lot of these things. I mean, the symbols, mathematical symbols, because in text we're working mostly with symbols, not with the images. So sorry, you will be seeing this most of the time. But what is going on here? In diffusion, we have Q for the forward process. So it is pretty simple, and it's what is important. It's Markovian. I think everyone knows what is Markovian, but just in case, what is Markovian? You know Markovian? Not everyone know Markovian. Maybe someone asleep. It's okay. So Markovian, that means that it's named after the famous Soviet mathematician, but the main idea of the Markovian is that we have the process which is dependent only on its previous state. So our present depends only on the past and not on the future. And the degree of the Markovianity, say, it depends on how long the past you consider. So here we depends only on one step back. So it's first order Markovian process. And we define the Q as the multiplication of this Q for each step. So Q xt for xt minus 1 and it depends on q xt minus 1, xt minus 2, and so on. This is for the forward process, and for the reverse process, it's kind of the same thing, a bit different actually, because we have this additional thing here. It's probability of the final state xt, and other thing is the same, but what is important, this p probability is given by this theta parameter. So we parameterize this function and we learn this function. This is kind of given to us since we already seen it, and this we're hoping to get from the data. Okay. The most of my talk is and most of the diffusion models is actually about these loss functions. And the loss functions, they actually looking terrifying, but they pretty simple if you look inside it. Let us try to decompose the function, and we are now discussing this variable lower bound loss, which is used in the most cases. So we have an expectation on Q, the forward probability model, and we have these three parts. The third part is the divergence between the xt, the final state, and x0, the zero state, the state we actually want to know. This is the q and the divergence between q and p, and this is for the time step t big, the final step. And for the all other steps except in the first one, we have this stuff. This is the again the expectation, KL divergence, Kullback-Leibler, of course, KL divergence, and the same with the Q and P theta, but with P theta being x t minus 1 xt. And the final step, or the first step is better to say, the first step is again the expectation, but here we have only the logarithm for the p theta, because this is like the final state. We have no distribution of the data here. No distribution of the data which we consider here. Okay, so how we actually get this Q and P? Because Q and P we need to somehow get to be optimized, and this is not really easy stuff. But in many cases, the diffusion models consider Q and P being this stuff. Q will be normal, or I mean Gaussian distribution, xt multiplied by this 1 minus beta t xt minus 1 and beta t I. Let us describe what it is. This is this is the covariance. This is the how to call it, the sigma. It's a sigma, so it's how big it is actually. And what is important here is that beta is just you can think of it as just a parameter which we use to somehow model the lowering lowering probability of the next step. Okay, so regarding the p theta, the p theta is also normal distribution, but in the other way around, and we now being conditional on mu theta xt t. What does it mean? Mu theta, it is the mean of the distribution which is produced by some model which is inside of this theta, I would say. So it's behind the thetas. Let us think of this as some neural network which is producing for us some distribution, and we get the mu and we get the sigma for this. And mu and sigma depends on xt and t as a time step, of course. I don't know. We do not allow the questions during the lecture, or we do? Mostly no. Okay. But if you really want to ask something, please do. Okay. So this is how it actually was done. So we somehow created these probability distributions for us. So we choose the family of the distributions and we try to get the distribution. But the issue is we actually working with text, if you remember still. So if we are working with text, the text, they are not continuous. This is the main issue here. And actually, we can solve it in two different ways. This is the one way. The other way I will show in a few slides, maybe not few. But let us consider here the first thing that we have the categorical distribution. Why we need categorical? Because texts are discrete. Because we have a specific word, and this specific word, it is the discrete, the only word that it can be. It cannot be smoothly go to other words. For example, we cannot smoothly get from cat to dog. We need to switch explicitly from one to the other. And well, when I say switch, what I mean? I mean that switch, that means that we have this Q matrix, and this Q matrix, it actually contains some probability of jumping from one to another. What does it mean? So let us consider that Q is a matrix which is the size of a vocabulary. Of course, vocabulary is could be huge, but let us say that for the experiment, we have really small vocabulary of 100 words. And we have matrix 100 by 100, and we have a probability which is lays on ij cell that we jump from the j to the I. So this is a probability of jumping from one state to another. In other words, it's from changing one word to another word, from cat to dog, let's say. Okay, hopefully you get the idea of jumping all around here. So the next thing is we'll be trying to get more letters here. So let us say that we try to get the qxt conditioned on x0, and this is categorical distribution by our definition that this is xt and probability that x0 qt with a line. Qt with a line is just the multiplication of all the q's since the beginning to the qt. So it's actually the huge matrix multiplication. It could be really long. For example, if we have a text of I don't know, length of War and Peace, it will be several hundred thousands of multiplications. Of course, no one is actually generating War and Peace with diffusions, but still. Okay, and for the other steps, not the final one, what we have here, we are getting from xt minus 1 to the xt to the next step. And here we have the q xt minus 1 x0. This is actually bias rule as it's it. So q x t minus 1 conditioned on x0. So this is in the end just categorical distribution. The probability is xt qt multiplied vector by vector x0 qt minus 1 and actually in the and below x0 qt xt. So the main idea here is that we multiply x by q, what time we need, but let's say for all the time we need, and after that we divide by the x, q, and x. So this is also vector multiplication here. Okay. When I was saying to you and showing to you the different possible matrices of jumping all around the vocabulary, we can define these matrices in more formal way. And here what we have, the qt here is 1 minus, it's a constant, not important, bt, if I equals j, and 1 by k bt if I do not equals j. So this is uniform. And what does it mean? That means that the most of probability mass is on the main diagonal. In the all other probability mass is really small and really smooth on all other cells. Hopefully it's distinguishable from the formulas. And for the absorbing state, it's 1 if I equals to j and to m, and the other stuff is 1 minus beta t if I equals to j but not to m, and bt is I equals to m and I is not equals to m. What does it mean? Does it mean that we have main diagonal and we have the we have other two lines, the horizontal and the vertical lines, which are adding to us some of these absorbing states. And finally, we get the loss. As I said before, at least I wanted to say that in all of the diffusion models, the most important part, at least up to now, is how we actually computing the loss. Computing the loss, it is like we have this our variable lower bound loss here, plus the loss on the entropy loss of this p theta distribution. This is actually not exact p theta. This is p theta we get from the sampling the model, but it's not really important here. So we get the distribution, and we get the expectation on q t conditioned on q0 x0 and q x0. So this is like normalizing part of this formula. Okay, so let us return to the results I've shown you in the beginning, and let us consider it a bit more closely. And what is more important here is that we can see that we have different types of models which are presented on the left graph. And what is this is that we can see that the perplexity is going down with the number of inference steps. This is not really surprising, because it's what is expected to do. But before that, who knows what is the perplexity? For some reason, not everybody. Okay, let me describe perplexity in a few words. So in a nutshell, perplexity, it is how surprised the model by the next word. So it is, what does it mean? It means that if a model is not sure about the next word, the perplexity is high because it's do not know what is coming. If the model is 100% sure, then the perplexity will be 0 because there is no surprise in that. In the human conversation, the perplexity is actually low. I could give you the numbers, but it's not important. It's low, but it's never 0 because I always can use a few ways to say the same thing. So it's always have some variations. It always have some value. But what's important here is that we see if we use different types of the matrices, of Q matrices, then the perplexity is different. And what does it mean? That uniform matrix is actually worse than the masking matrix. Masking, which is it's so let us say this is a kind of absorbent state. And we can see that it is better for some reason. And this is, again, the same. And if we look here, well, we can see that this is the original, what we started with, our training. This is what we want to actually reconstruct. We corrupt it, adding some masks, and we reconstructing it, so we relieve the masks and getting the sentence readable back, and we want it to be as close as possible to the original one. So it is the corruption is the forward process of diffusion. So we add in some masks, and these masks are actually a diffusion. They worsen our text. And when we're reconstructing, we're making the reverse process. I'll say a few words about that later. Okay, let us discuss a few results here. So the model we are discussing called D3PM. So it's a diffusion sampling model. And you can see there is 3 types of this diffusion model. So the uniform diffusion. Uniform is, as we remember, the main diagonal. And the second one is, second one is neural network. And the third one is absorbent. We discussed uniform and absorbent, but neural network we haven't been discussing. And this is just, let us say this is just learned. So we just have some neural network which is learning how we actually want to jump around the diffusions. And as we can see here, if we are comparing the numbers, then we can see that the numbers are actually pretty high. As I said, the perplexity is the degree of surprise of a model, which is while the generating text. So higher perplexity is, the worse. And we can see that uniform is better than learned metrics for some reason, and it is worse than absorbent state. But what is more important, the transformer, transformer XL and transformer XL is just a model. It's not important which one. It's much better than the others two. Also, what is important here is that the time we're actually spending on the generation. Why it is so? We have already discussed, and Denise has said a few words about that, that when we have a diffusion, the diffusion could be, it is actually optimization. So we applying some function which is getting from our actual distribution to the desired one. And we can go there by small steps, applying this function a lot of times, or we could go there by huge steps, applying the more aggressive function. But if we apply the more aggressive function, then we lose quality. For example, if we apply only 64 for this paper, 64 steps, the time is actually good. It's faster than the transformer, but the quality is much worse. If we apply the comparable time, if we apply the steps, which gives us a comparable time, like here, then we get the results worse, but a bit better. Okay, so and what I could also draw attention to is that if we use neural network for the generation of this matrix Q, then we get not only the worse results, but also we get more time spent. So this is why it's not actually really useful in the diffusions. Okay. And I actually said that, well, I will be giving you more details on the diffusions. And this is what is really interesting. We could reinterpret all the existing models for the standard language modeling. Standard, I mean, the masked language modeling for BERT, or the classical language model, which is called causal language model for example, GPT or something. Then what if we reinterpret that the BERT is actually one-step diffusion? So we say that BERT, if you remember how the BERT is actually learning, it's applying the mask on the data with like randomly replacing 15% of the data with mask or something else. And this is a one-step diffusion. So we just trying to resolve these masks. And this is just one step. If we are talking about the generative models like GPT or something like that, then we have these many steps of diffusion, and these many steps will be like the number of steps in the this number of tokens in the text. So if we have War and Peace, we'll have a few thousand steps. Okay, so that was the basics here. And let us discuss a few papers regarding the diffusions from few years back. That was a paper from 4 years back, and that was like the first, I would say, successful paper, but not many papers have been developed in this direction. After that, we'll be discussing diffusion LM, which is also has a huge influence on all the stuff which is going on right now. Let us have a look on the diffusion LM. But what is the difference here? We have the states. Yeah, so we have the Gaussian noise. we have some denoising process, or noising process if you want, if we are going back to the in the back direction. This is the denoising with this p theta function, and we come to some 0x state, which is the well, and what is this? Is this important? X0 is an embedding. So this is another approach to the generation of texts with language models. So as I said, there was a first approach, and it is kind of obvious when we are actually producing texts like the discrete tokens, because text is always discrete. Producing discrete tokens has its advantage. You just get the words you want. But the disadvantage is that you need to somehow understand how to handle all these huge Q matrices for the vocabulary. Another approach, which is also possible and kind of successful, is this approach when we actually getting the distribution on the embedding. So we actually predicting the embedding itself for the words, and since embedding is in continual space, it's much easier. But in this case, we have another issue, and this issue is that if we actually predict an embedding, how we get the words back. So we have a bunch of numbers. We need somehow the words. At least we want from our language model to generate language, not the numbers. And here is why we have so-called rounding. And this rounding is actually getting us from this predicted embedding to the closest word embedding here. Okay, so the diffusion LM is a bit more complicated model because it has an additional part. Let's say this additional part is that they want to have this generation be controlled by some external thing. It could be other model. It could be some algorithm. It's not really important. If it's another model, of course, we can get the gradient. So if we have the diffusion, what we have? We have the Gaussian noise, and this noise has been gradually denoised by our models. And on each step, we get the classification on the produced embeddings. We have the bunch of embeddings here. And we classify them and getting the feedback from the classifier to get better representation. So as I said, in all the diffusion models, the most important part is the loss function. And loss function here is this is actually the standard standard PL function, which is just written in this way. So we have an expectation on the Q. So we have logarithm Q on P theta plus sum of logarithms Q P theta for the other steps, and the last part is for the final step. As we all remember, it's all the same as I was presenting, but these guys who wrote this paper, they actually used results from the other article, but in this paper they use other loss function, which is they call L simple, and L simple is pretty obvious. So they somehow derive it. I will be not discussing to you, discussing with you how they will derive it, because it's really far from our topic. But they shows that this could be simplified to just this. So we have some of the expectations over the time steps for the norm between mu theta minus mu mu from the data. So we get these two mu's, and this mu, as I said, is mu from the distribution that produced by the model or by the data. So we want to minimize these two mu's. So actually what they are doing, they just saying that we can somehow predict these embeddings, which will be close to the embeddings which already pre-exist in some way. Okay, so that is not enough, and we have some end-to-end training objective. That was simplified one. The end-to-end, it's when we add to the VL the entropy. We get the entropy of Q and subtract the entropy of P. If we simplify this, we get the L simple plus the embeddings for the first step, and again the entropy for the P. So it's much more simple than before, because all of this stuff we already knew or can get easily from the model. We can get the embeddings, we can get the distribution from the model, and we can easily compute it. So all of these tricks are just for ease of computation. So the generation itself, how they generate it. So if we get the in the way of reverse process, and the P of C. So this is for the classification, as I showed on the picture, and this is for the diffusion model itself. So this is how we get the gradients for the controllable text generation. Okay, so what we get here, and what they wanted to get here, they wanted not to measure the perplexity. We have discussed with you the perplexity is a really simplistic measure. We just measure if the model is surprised by the next words, and that's it. It's actually not really enough. In our text generation, like in the real world of text generation, we want to generate some word which will be which will actually generate something we wanted to generate. For example, this is I forget which is the data set here, but let's say this is movie reviews. I don't really remember exactly the data set, but we have several measures. So the rouge and blur and rouge, they are from n-gram. So they're comparing directly which tokens are in the generated text and the original text. And as you can see, the blur score is the highest in their, of course, in their setup for the diffusion, and it's even better than the autoregressive approach. That means that they just use a transformer here. And rouge also is better. Cider is also about the n-grams. And BERT score is totally another thing. BERT score, it's comparing the embeddings of text. So when we feed the text to the bird get the embedding of the text, and we compare these embeddings and say how similar the embeddings are. And we see that by these measures, they're on par. Actually, maybe a few words about that, because I'm saying on the one part about the tokens and another part about the models, and it seems to be that these metrics are actually not really the same, and they are not the same, but we as a community know that token per token metrics, like Rouge or something, they're not really good, and the expression of variability of human language. While the BERT score is better on that, but it cannot get the differences in some easy mistakes. For example, if I'm saying that I give this, I don't know, I give 100 yuan to John, or I give 100 yuan to Jack, for Bert, it will be almost the same. But for John and for Jack, it will be totally different, as you understand. So there are these, we need both the measures of tokens and the measures of semantic similarity kind. What is also important here is that we have this human evaluation. This human evaluation they have done, they try to ask the people if they like the generation or not, and they show that actually generations are almost have the same almost the same result in regarding to the statistical difference. Okay. So the next paper, it was pretty interesting, and it is pretty interesting. It was pretty famous back in the day, and maybe 2 years back. It's Genie from Microsoft. This Genie model is actually pretty simple. In comparison to what I have already presented to you, it's pretty simple. But what is important here, it's actually working in another way. What we have some encoder input words. We have encoder, which is also transformer. We have the output of the embeddings from the transformer. You see again the embeddings, and these embeddings are actually coming to the language diffusion model, which is used them as the prefix. Sorry, not the prefix, as a cross attention. It's like the conditional, as a conditional, yes, as a conditional here. And we use this as a conditional. Why? Because actually the diffusion language model here is a transformer which is producing the also embedding. So we get the initial Gaussian noise, we get it to the transformer, get the condition on the actual text from the encoder, and output some other embeddings, which could be feed back to the same transformer blocks a few times. This is actually steps of diffusion. So we have several rounds of this diffusion, and finally they actually been fed to the decoder. Of course, it's also a transformer, and this transformer is getting the output, its generate output. So this is what is the difference. So we have actually a whole transformer here, but instead of simple decoder and the encoder, like encoder and that decoder here, we have in the middle the language diffusion model, which do some diffusion stuff. So it will possibly improve the quality. Let us have a look on the improvement. So what we have the results here. As you can see, we compare with pretty old models, but there are the For that time, they were not so old, but still. For example, this BART model, simple transformer, and stay on something. But if you can see that this diffusion Gini model is better in the most cases than the other models. Of course, maybe it's not really not really honest comparison, because these are, as I said, pretty old models, and now we have better models for generation. But since that we have the diffusion models which already generate good, and as I said, we see here this n-gram matrix. So this is Rouge. This is also Rouge of different type for two different data sets. One is CNN Daily Mail, and another one is Gigawort. CNN Daily Mail is and Gigawort also there for summarization. So what does it mean? That means that we feed in the encoder the whole article, news article, and we want our diffusion model to produce a short summary. And you see that it is better. And what is also important, that in Gini, they use pre-trained decoder. That means that what they have, that they used, I don't remember which exactly model they used. I think it was T5. And they just get T5 model inside their diffusion model and train diffusion model not from scratch, like in the penultimate row, but in the ultimate row we have the better results. So if we have the good pre-trained model for generation, it is helping to get better results. This is an important point for all the next stuff also. Okay, so another work from Apple, it's called Planner. And this Planner model, what they actually wanted to do, they tried to solve the issue of the early models. You can see this is from GPT-2, I think. This it's not actually said here, but it's fine-tuning of GPT-2 model. And for the early generation models, there was a huge issue that they wanted to repeat themselves really often, would say. And what they would want to get rid of this, and they said that their diffusion get the much better results with almost no repetitions. And how they do this? Actually, they do almost the same thing. If you remember the Gini, or you think of the diffusion models before, it is almost the same. So we have the encoder when we getting the text in the sense of tokens into embedding. By the embedding, we have the some representation. It is distributional representation of this text, and this embedding is used for the decoder to reproduce the same data. So they want to reproduce these words with the decoder, and this is actually autoencoder. And what they actually want, they want the representation in the middle. Why they need this? They actually need this because they want their latent diffusion model to work with it. So what is here is here we have the we have some prompt have been embedded in some in some way, and this way is used in transformer model, like in the Gini. We use it with some cross attention stuff with a transformer model, which is actually being the diffusion model here. So it produces this, that, which is actually the same as the output of the variational autoencoder. So we produce the distribution on that, which used by the decoder, the standard transformer decoder, to actually produce the text. And what we get the results, as we can see, this is also CNN Daily Mail data set. And we can see that the planner is better than the Gini. But it's not really better in the Rouge sense, at least in the not all the Rouge sense, but better for the other stuff. So these models are pretty the same with some differences they have, but they use the main idea that we can reuse the already existing data set, existing model to get the better results with our model, with our diffusion model. We'll not be discussing exam because it's also summarization data set, but maybe it's not really important. Okay, so that was like the other day. So what we have maybe a few years back. Why I actually decided to have this lecture with you today? This is another stuff. This is Lada. I think people from Russia know this word. It's a famous Russian car brand, but the guy is not from Russia, unfortunately. And what is the Lada? Lada is language diffusion, which has 3 steps. On the pre-training, we just trying to mask some any words we want and trying to reproduce them. On the next step of fine-tuning, we are not masking prompt and masking only response and producing the response only. And on the actual how to say it, inference, we get the results. How we get the prompt, we get all the data set, all the text masks, and we masking it several times. This is really important because I already said the word about remasking, and we now here can discuss it. So what does it mean? That means that our model is actually can leave mask from maybe one word, and we remask. That means that we adding another masks on our text to generate more words. So we mask it in one way, we leave few tokens not masked, and we get these tokens, and after that we get another mask and another mask. This is the diffusion steps here. So as a step, this is as I said, this is the same with the text. So we get the diffusion step by step, flexibly remasking the tokens. And as always, the important part is the loss. And what is interesting here is that for the Lada only, their innovation is that they are remasking, or sorry, they are like getting predicted all the tokens at once, all the masked tokens at once. So they're not predicting by one token as before. They're predicting all the tokens we want. Of course, in practice, they cannot predict like the whole War and Peace. They can predict maybe 5 to 10 tokens at the same time, and this is why they need remasking. So they mask these tokens and predict them, mask another tokens, predict them, and so on. This is about the results. And LADA is actually comparing with Llama 3 8 billion, because LADA is actually Llama 3 8 billion, which is also like fine-tuned as a diffusion model, and with Llama 2 7B. And if, as you see, in many cases, not in all, unfortunately, but in many cases, LADA is better. So we will not be discussing the quality here in all points, but we can see that LADA is actually either on par, either a bit better in many cases. Okay, the next paper, it's actually a bit old also, but you will understand why I show it here in a few slides maybe. The idea here is that this reparameterized discrete diffusion model, or RDM for short, is introduced here. And what is the main idea here? The standard discrete diffusion, when we have x3 with jump to x2, x1, and so. And for reparameterization, we get this additional input v3, v2, and so on. What is giving us, I'll show it to you in a few seconds. But more importantly, this is actually a graphical model. So that means that this state is depends, let's say x2 depends only on x3, and that's it. While x2 here on the lower RDM model, it depends on v and x3. So this is more like hidden Markov model, if you know what I mean. Okay, so for RDM, what we actually want, we want here to do what? Q here is the same. It is forward diffusion, but there are two types of this Q. So if we have the Q on the final step, it's just noise. If some other steps, it's the noise which is conditioned on X. And also there is some additional stuff with constants. I just leave it here for reference. What we want, we actually want reparameterized sampling. So we have this B, which is indicator function if X is equals to X0. We have this V being Bernoulli driven from Bernoulli distribution, and we have actually two V's, the V1 and V2, one being from the noise exactly, and another from being from the noise conditioned on XT. This is how it goes. So we get the XT minus 1. This is B, so this is our indicator function. So it is either this xt minus 1 xt, vt minus 1 xt minus plus 1 minus v ut, and we'll discuss ut here. It's ut is from here, and all other way around. So it's either from the first distribution or from the second distribution. And essentially, B is given is saying to us if this token is already been denoised or it's not yet. And if it's yes, then we use the first distribution. If it's not, then the second. Okay, so what they want the joint modeling all this stuff. So it's x conditioned on v x t x 0. And as you can see, it is the same as the previous, but maybe more fancy written. So we can understand that next x will be dependent on either bt is already denoised or not. So again, all this stuff about the loss, they simplify their loss in different way than before. They again get the estimation, but they have this xt log f weighted by lambda, and this sum is about all the steps from the from the diffusion. So what we have f here, f is just the logits, the output of our function, and lambda is just waiting, as it was shown on some of the previous slides. Okay, how we get b? B is, as you can see, is just getting 0 or 1 by using conjunction or disjunction with this b stuff from the previous step. Okay, so why I used RDM? Why I showed you the RDM? Because this is the paper the model DREAM is based on. The DREAM is not a paper; it's just a model which has been produced by Huawei. And their main innovation here is that they use the diffusion in the specific way. So they have this, again, remasking as before in LADA, but their remasking is somewhat different. They remask basing on the model, how to be said, on how model unsure about this mask. So if this if it has a huge entropy, for example, this token has a huge entropy, then we actually choose it to mask or unmask. It depends on what we actually want. So this is they actually use two types of these entropy for token level and sentence level, but it's not important. More important that the DREAM is better than LADA in almost all the, or maybe even all the data sets they have compared with, and it is already good. So it's really good, and it is on at least on par or even better than the some of the data sets, some of the models like standard models. Another somewhat old paper, which is representing the approach which is called CEDD. It's a bit complicated, but what is this? This is we already discussed Markov decision process, but they show it in a bit different way. So they say this is Markov decision process given by this ordinal differential equation here. It's almost the same, but what is important, we have these differentials. So we have somewhere we have the integration, the future. And what we have here, again, this is always about the loss. And for the loss here, we have this concrete score matching. It's like Fisher divergence. It's Fisher divergence. It's another divergence, not the divergence as scale divergence. It's another way to measure the difference between two distributions. And as you can see, S here, S theta is the rounding on the the condition on the y over px. And here we have the difference between them. This is discrepancy of these two distributions. And we use the entropy of this discrepancy. And this is almost the same, as you can see, but we have this constant, which is not really important. And we have the weighting here, or the entropy. They actually used denoised entropy, so they said that that entropy was really noisy, and finally they wanted to weight this entropy. This is the same entropy on the previous slide, but weighted by this Q matrix. You remember the Q matrices? They use this Q matrix and reweight it, and Q matrices, as before, could be uniform. It could be absorbing state, and as we could use as simple as just counting from the data. And what we get here, we get sorry, this is about the practical issues. So we cannot easily compute huge Q multiplication. So this is why we actually use the exponent, and we use just simple differential over sigma to get the easy computation. They say that this becomes worse, of course, but it's still working for their stuff. And what does it mean working? They said that their model is actually better than GPT-2. This is important. GPT-2. They compare them to GPT-2. It's not really even at that time. It was not really fancy model. It's not new, but they compare the model, small model only, because they cannot make it bigger. But it is comparable in some ways. This is also the perplexity as before. But this is why I actually wanted you to show this pretty old paper, because this paper, which is pretty fresh, maybe last week, it is Mercury. It's technical report. It's not paper. And this technical report, I personally really don't like it, because exactly what they say. They say that all we have this from this set paper, and we have our like private proprietary inference engine, which allows us to sampling faster, and this is why we're so cool. And that's it. So the results they show, as you can see, they're really almost on par with big models like GPT-4 or something like this. And they actually much faster, up to 10 times faster than the big models. So their inference engine is pretty amazing, but they do not show it to us. And I think finally, what I want to discuss with you is also really fresh paper, also from the last week. It's called Diffusion. It's also from Apple. And again, we have these results showing who is the best here, and you can see that the Diffusion is actually better than all the models it compares to: the LADA, the DREAM, and the Gemini Diffusion. Gemini Diffusion from Google. I actually do not know to show you about it something, because it just happens. I mean, it's just exists, and I have nothing information about what's inside. And here you can see how it can be generated. So it's generating code like in the beginning, we generate a few words in the beginning. Next, we generate a few words after that, and we jump to the end. And we jump back, and the last words have been generated in the middle of the text. So it's how it's called, how it's generated. The Diffusion, the most important part here, how they actually work with it. They take the Qwen models, they pre-train it on the on some data sets. After that, they make the instruction SFT, and they make the GRPO. And this green stuff, it's already diffusion. So it's a diffusion stuff, while this is the standard cross entropy stuff. And they actually use the GRPO. GRPO is a RL algorithm. I mean, reinforcement learning algorithm. I'll be not discussing it with you, but the algorithm is they actually presenting the modification of this GRPO, and it is shown here. What is interesting, they just divide it by two blocks. One half of the tokens randomly masked in one part, and simultaneously the same tokens being not masked in the other part. So it's like they're complementary to each other. And they say that this is these two steps is enough to get better results on the other stuff. This is the actual GRPO modification they have. Sorry, this is the GRPO itself. So it's easily like raw. It's like difference between two models' behavior, like our learned model and our old model. And we want it to be not really far from each other. This is standard Kyle divergence. And they modify it with actually pretty simple stuff. You can see this L. As I said, this is always about L. And what is L here? L here is just delta, which is indicator function. And F is, again, the logit. So we just adding a few diffusion steps inside the GRPO laws. And given that, we're getting the best results ever. And I think I missed the slides with the results for this model. And so that's it. Thank you for your attention. I'm finished. Any questions? I hope not everybody is asleep.
Yeah, thank you very much for your lecture. Yeah, could you please clarify some initial stuff? In approach, when we learn matrices of conditional probabilities, transitional probabilities, so we have matrix for each token, and we end up with tensor for our full sequence. Yes.
Actually, your question means that I haven't done my work well. So let me, in a few words, say it again, maybe better. So the idea here is that the matrices of the transition, diffusion matrices, they call this is Q matrices, they are fixed. What we actually learning the model, which is actually applied to the distributions to make it look some way as we want. So we are learning the function which is shaping the distribution, not the matrix for the token.
Okay, so if our transitional probability is fixed, where we can obtain them? How?
Sorry?
How can we obtain them if they are fixed?
So let me go back here. It's maybe in the beginning, so it will be easier to get. So the Q, we need to discuss Q here. Is as you can see, they are fixed in a way that this is constants. This is actually constants. The Q is fixed, but the Q as a distribution, it has this maybe it's here more understandable. So here we have the distribution which is based on X, the input data, which is always different, and Q, which is fixed in a way that it's like with each time step, it's becoming a bit more more smooth or something, let's say. So X is different while Q is fixed. So this is why the Q as a function is always different.
Okay, thank you.
Thank you for your question. Any more questions?
Thank you for your interesting report. I have a question about the Gemini diffusion. What do you think how it's trained? Because how it trained, what the principle of diffusion inside of, what the principle of encoding of the text embeddings and so on. Because I didn't see the technical details about Gemini diffusion. Maybe I just missing.
You're not missing because I haven't seen it too. As far as the state, they haven't published the report. Maybe I've missed it, but I have the time to get a look on that. But I have some like I have some thought how they can train it, but I cannot be sure. I think that they also use something like this Mercury model. The idea is that we're producing the tokens in the discrete way, but we use the some good pre-trained transformer model inside to be to be this function which is actually predicting to use the distribution shift. So I suppose they use this. Maybe they experimented with gamma. I'm pretty sure that they've seen something about gamma and diffusion, but I cannot find it maybe anymore. And they put it inside the diffusion model, and what they actually want, I think what they concentrate on is the efficient sampling. And efficient sampling, we do not know how they do it. So the stuff about the generating itself, it is already a standard. So we just have transformer model, and which is actually predicting to us the distribution shift for the to generate the actual text. But how to sample really fast, we still don't know as a community. Thank you for your question. Other questions? Seems to be no. Then thank you again.